Okay, so let's continue with our next speaker. Our next speaker is Anand M. Shrivastav. I hope I said it right. That obtained his PhD in physics from the Indian Institute of Technology in Delhi in 2018. And currently he's working as Marie Curie postdoctoral fellow at the Public University of Navarra, Spain. He has worked on several research areas, including SPR, LSPR, SERRS, optical fiber interferometry. And his current research area is focused on Lucy mode resonance-based sensors for biomedical applications. And in his presentation, he's going to talk us about designing considerations for planar Lucy mode resonance waveguides and the effect of substrate properties. So please, Anand.
Thank you, Carlos, for inviting me. And as you introduced me, I'm Anand M. Shrivastav, and I came to Upna in November. So there are almost 6 months when I'm in Upna. So I did some work, and which I will present here. So my work is basically focused on LMR on a substrate. And before talking about my work, I will just give a brief about my research areas, what I did from last few years. So my whole research is basically focused on healthcare application, detection of several biomolecules, biosensing, air pollution like gas sensing, water quality monitoring like monitoring of the metal ions in liquids and all. So there are several techniques which are in the right now in people working on these things, chromatographical methods, electrochemical methods, and mass sensitive methods and optical methods. And I'm basically working on optical methods. So there are 4 key areas I'm working. My main work, like lots of work, is focused on plasma sensors like SPR. When we use a metal film, and then we have a sensing layer on top of that. And currently, we are working on LMR based sensors. So LMR based sensors is just basically you take a optical fiber and over the fiber core, or you have a coating of a metal oxide or some material which have high index then core. So light get guided through the core medium, and you have lossy modes in there. And when lossy modes and core modes they have matching phase matching, you will have a resonance. And at that condition, you will have a sharp dip at certain wavelength. And since this dip is very sensitive, as the dielectric constant of the overlayer changes, like if you change the dielectric constant of overlayer by delta ns, you will see a shift. And by monitoring the shift, you can tell that there is something interaction is happening there, and you will see a shift. That's why we use there for some many application like biosensing, thin film characterization, like you can use the to monitor the thickness of the film and all the roughness and all these things by different method of deposition, spattering, and all these things. Physical quantity like reduction of the temperature, humidity, and our group had a lot of work on these things. And since then, also for biosensing like chemical application and food safety, it has many applications after that. So a lot of work our group have done on optical fiber sensors using LMR, and last few years we are moved to the planar substrate. The reason behind the substrate are they give the more tunability in the performance. Like you can use different material like glass, cover slips, PFA, PDMS, like which is the polymer having the which can guide the light. We can use them to find the optimized results. You can change the many parameters like thickness, line, length, width. You have more tunability compared to fibers. Also, you can use several type of configurations, like you can use the dual LMR, which were our group had reported, and then the sliced LMR chips, like you can add. You can combine that together, LSPR and LMR together on a single substrate. This is why our group more focused on planar waveguides, and also it's easy to use some functionalized layer, like you can use antibody compared to optical fiber. It's much easier. It's much easier to work. That's why our from last few years we are working on the planar waveguides. So my objective is that as we know that our group have reported that very high sensitivity around 41,000 nanometer per RIU from waveguide structure, but the problem is the depth. You can take about you see that around 10% contrast is very less, like 10%, 20% maximum studies what we have seen. So my objective is first to check the effect of the waveguide. We have done a lot of work on the top layer, like using different type of LMR layers like ITO, SNO2, indium oxide. There are many work we have done, but our focus is now to see the effect of the waveguide. And then in the waveguide, first of all, effect of the spot size of the light, which is hitting the interface. Second, the effect of length and width, and also the refractive index, and what are the possibilities there. And after that, when we see the optimized result, then we will design substrate which is most useful for us. So for that, we did some studies, and first study is effect of the spot size. So in this case, we took the marker here, like this one. Okay. Oh, yeah. So in this study, we use the waveguide of silica SiO2, and then we have a LMR layer of titanium oxide TiO2. 0.005 is just is the imaginary part of the TiO2, and then we have a surrounding layer of 1 to 1.1, like index of 1 and 1.1, and this is the bottom layer of PFA. Just a substrate over that we can put the your waveguide. So what we saw that by effect of spot size, I used two type of spot size, 8.5 and 200. So you see for 8.5 we saw a more deep LMR compared to the 200 micron like 200 micron spot size. And this is the in terms of power, and then in terms of transmittance. So we saw that spot size is smaller, it is much useful for us. The reason we suppose that when spot size is less, the less number of modes are propagating in the waveguide, and that's why we are having more sharp curve. Again, we changed the thickness of 150 to 30 micron. So now thickness is less. So now we see at the transmittance curve that there is no such effect of spot size. The reason actually what we expect that since the waveguide is like sufficiently small so that it can propagate efficiently modes which are possible, which can contribute to LMR. Like suppose your waveguide is 150 micron thick, so the main important mode which are interacting to this layer, it is only at that part only. Like it means that only some part of light which is interacting to the top layer. So now the thickness of waveguide is sufficiently 30 micron, which is propagating all light. So effect of spot size is not affecting much. Second part is the waveguide thickness. Like we used silica waveguide layer, and we changed the thickness from 10 to 70 micron, and we saw that the depth of the LMR is increasing. But after some certain values, because of these two layers, they have some interference. So for 30 micron width, we are almost zero. So in that part, all part of light goes to top layer. That's why you see higher contrast compared to the around 150 micron width of LMR. And also the good thing is that it does not affect the sensitivity. So this is the first thing of waveguide thickness. Then I try to change the waveguide material. Like here I am using PFA, and here I was using SiO2. In PFA we saw that around 30, again around 32 micron, around 30 micron we saw the same results, like around. Oh, here is not in terms of power. Actually, we should plot in transmittance. It's almost zero also. So here the sensitivity increased, but the contrast is almost same. So here also the optimized is around 20 to 30 micron. Again, for PVA, so in this case also we found that the optimized thickness is 20 to 30 micron of substrate. So this is what we found that the optimized thickness of the waveguide around 20 to 30 micron, and in this thickness we got the contrast of near 0%. Like all light come to the to the over layer. That's why you see a very high dip. Then we also did an experiment, some simulations to find out the waveguide effect of waveguide length, whether it is 200 micron or 10 millimeter. So what we saw that for 200 micron, it's very less deep, around 100 to 90 only. But for higher length, you see a more deep curve. Although we have to pay for the very wide LMR. So this is some overall study. Like we fixed the substrate of the 20 micron silica, and we used defined spot size 8.5 micron, 62 micron, 200 micron, and we found, and this is changing the LMR, like the length of the waveguide, like from 500 micron to 10,000, like 10 millimeter. So you see that as we go down, like the length is increasing, you see more deep curve, and this is because you have enough length to interact with the waveguide, and so we found that around the optimize is around 20 micron width, 8.5 micron spot, and then we saw a 40 millimeter full width of maximum, the minimum. Otherwise, this is like as you change the length, you will see a broad curve, but you will see more deep, but they are more broad. So it's like you have to pay for something when you achieve something. Like for 10,000, you have high full width of maximum. Then I also try to check the effect of bottom layer. I just use a random NS, like a substrate of 1.31 and one, like some gel 1.0, 1.02 aerogel. So the sensitivity is not affecting much, and full width is also of maximum not affecting anything. So it tells that there is no such effect of the bottom layer, because all light mostly propagating towards, you have enough thickness, so all light will propagate in this medium only. Then to verify our the experiments, then the final thing we found that we have to use substrate of PFA, because PFA has low index and they will give the high sensitivity. But and also you will get a high deeper LMR when you use the thickness of 20 micron. So our objective is now to verify experimentally that how high sensitive LMR using PFA and more deeper curve, so that we can get good contrast and it is much easier to detect. To verify experimentally, first initially I was trying with PFA. I will tell that what problem we found, but to verify it, I did experiment with cover slips, which is around 150 to 160 micrometer thickness. And what we did, we etched the the cover slip by using HF, and we found that since these are not we found that when we around etch till 30 to 20 or 30 microns, we see a more deep curve compared to the uh, to the bare cover slip. So here in this case, the dip is around 80%, but here now we are at around 40% we found. Then we try to monitor the etching, like we just put HF and we try to monitor the how dip is going down. So we found that around 10 to 12 minutes of HF, the etching, the all substrate goes breakdown, and that's how LMR curve goes more deep, and contrast is like around 70% to 20% what we found. Suddenly we saw a breakdown, like in that point the all there is no chip, everything finished, and the good thing is, like, not the good thing, I don't know. And the thing is, we don't see much effect of in full width of maximum. Like although you compare the width here or here, it is some effect, but not that much. The only thing is the change in the deep. So we have to find out why the effect of that, like how it is not so much effective, and the reason behind it, why they are not getting more sharp curve. This is all I did in last few months, and now we are actually trying to work with the PFA, which is 25 micron thick, very flexible substrate, And in this case, actually, we are facing a lot of challenges to do the experiments. The first challenge is we have to guide light with a thin substrate, because when you substrate is very thin and you cut it, at cutting you will have a very blurry sometime edge, and at this point the light get diffracts and it's not able to guide in the medium. So we are trying to find out a such very proper way so that we can guide light in the PFA medium, because it's very flexible polymer. And flexible is also affecting the bending. Like you put light, after some time, like you experiment, it bends and it don't come back to original condition. Then everything gone. So we are trying to how to handle with this type, this very flexible polymer, and also effect of heat when we are depositing to the in print of plasma. So it has it bends like this. Like you put heat and to the heat, it has slightly more bending, and it also affects our results. So right now our challenging part is to work with this polymer, because it has more possibilities, because it is more flexible. So we can use for many flexible type of sensors and all these things to find the effect of bending, what is happening in LMR, all these things. So this is the our next objective which we are working on. So this is very small work. I will just some theoretical part is some part of the experimental. So we'll see. And I also like to thank my all lab mates. They are helping me in each every time for all things, and also the Marie Curie Fellowship. Thank you so much for everyone, and questions.
Presentation, and also the great effort
Mm.
to concentrate all the experiments. I think there is a lot of work there in simulations and experiments in only 10 or 15 minutes. So please feel free. We have some minutes more.
Yeah,
You want to
it's very fast
to ask him some details, and you will have more time later. I think it's quite interesting and a lot of work behind this presentation. They are all astonished about your work.
In the group, so
Yeah, I have some maybe some question, quick question.
I have a small question. Do you have any specific application where you want to try your sensor, for example?
this sensor is it has right now we are working on effective index 1, so mostly for air. So gas sensing application we talk
For
about.
gases?
If we are talking about 1.33 index liquid, then for biosensing, but we are mostly right now focused for gas.
Thank you very much.
Okay, in these so flexible substrates, you get a losing resonance in the bend, the substrate. You will keep the resonances or not?
While bending, if light is guiding in the waveguide, we will keep for sure. Like if it is very bent, then if the angle of LMR is not satisfying, then we will not see. If we are getting the LMR, the angle is within the range of required for LMR, we will see the LMR. Yeah.
No, if you have an answer. You have presented the contribution of different things to the generation of LMRs. So the intermediate layer, the substrate, the thickness.
Yeah.
What do you think is the most important, or no? I think what is the most important parameter, for example, for to narrow the resonance, to get the deeper resonance of those you mentioned?
The most important parameter what we saw that is the thickness. Thickness should be around within 30 to 30 micron. Then only we saw a very deep LMR curve. And also the length. Length should not be less than 2 millimeter. If length is 20, like within micron size of 0.5 millimeter, it's not very good. We see LMR, but it's very little, like around within 10% or even less dip. Like if you see here for length, you see with the first is 200 micron, and even this is when I increase the imaginary part of the DiO2. If you go to even less, like which is the real is 2.005, then you see no LMR. Otherwise, so length is important, but not too much. Like 5 millimeter length is sufficient for a good LMR curve. Thank you. Thanks so much.
Much.